Thank you very much. Thank you for this intro, Frederick. So I am Aldo. I'm an associate professor in analytical sociology at Linköping University, and as well an affiliated associate professor in data science and AI at DSAI. And I have the true pleasure of hosting this session where Susan Murphy is going to, Professor Susan Murphy from Harvard University, professor of statistics and computer science, basically talk about reinforcement learning. And you are, Susan, leading the Reinforcement Learning Lab at Harvard, and that lab encompasses or has two aims, basically: constructing individualized sequences of treatments for to be used in clinical decision-making, and secondly, construct real-time individualized sequences of treatments, just-in-time adaptive interventions using mobile devices. So the title of today's talk is that we used reinforcement learning, but did it work? Well, I'm very curious to hear if it didn't work.
It's great. It's great to be here. I'm going to share my screen. Okay, so you guys should be able to see it now. Yeah. Okay, great. Thanks so much for this invitation. I wish I was in Sweden. I love Sweden. All of you guys are very fortunate. So the reason why we got started on this work is in progress, and we really started down this path because we ran an RL algorithm, and it's very easy after the algorithm is run on a set of, in our case, users, individuals in a trial, to make a number of misleading statements. And this work is coming from that concern. How do we prevent ourselves from over-promising? So we're going to go through this. So these types of studies, they involve big teams. You need software engineers developing the app, behavioral scientists who come from the domains. You saw on the last slide, we work in a variety of domains in mental illness, addiction, and in cardiovascular disease, also in chemotherapy. So I have pictures of behavioral scientists here, statisticians, computer scientists. Kelly Zhang, for example, is a PhD student here in CS. Peng Liao is a former postdoc. What I'm going to do is, I'm going to use Heart Steps, which is a particular digital intervention. It's the one I tend to use in my talks because it's one of the easiest for me to communicate about. And I'll start with that. So this was a series of 3 studies. They're all over now. And the goal, but this particular project, Heart Steps, is continuing on. For example, right now it's being used in Southern California with individuals who are struggling with obesity. So originally, though, the intervention was developed for individuals who are at high risk of coronary artery disease, in particular, hypertension. And the first study was only with people, it was a 6-week study only with people who were sedentary. And then the last 2, which are the focus of today, were studies with people who had just been diagnosed with stage 1 hypertension. And that's a critical time at which one might be able to avoid medication if you're able to successfully change your behaviors, in particular, increase activity, improve your diet, and so on. You see there in all of these studies, each individual wore a wrist tracker that recorded step count and sleep quality, and then there were sensors also, of course, on their phone, their smartphone. There's 2 adjectives here. One is micro-randomized. You should be able to see that with my pointer. And the other is micro-randomized and personalized. And my goal is to make that a little clearer as we go on. So Heart Steps. So this is one particular intervention component in Heart Steps. All of these digital apps have many intervention components. There's 5 in the case of Heart Steps, 5 in which we experimented with. There's others that we did not experiment with, but we're going to focus on this particular intervention component. And at any of these 5 times, any of the 5 times a day, the individual could receive a notification And in this particular case, their phone would light up, and on their lock screen, you'd see the notification. And you see an example here on the slide. And this one appeared to me in the morning, a very cold morning, actually. And you can see how the content of the notification it's tailored to the weather outside, whether it's a work day, where I am at that time, and so on. The 5 times a day are related to each person's own schedule, morning, midday, mid-afternoon, and so on. We're going to focus on whether or not to send one of these suggestions. The suggestions are always contextually tailored to the individual's current sensor data, but our focus is on whether or not that suggestion is even sent or not at any of these 5 times per day. And this is what.
Sorry to interrupt you. I think there's I think the mic is hitting something at the table when you're shaking a little bit. So some people are typing.
It is indeed doing that. You know what I'm going to do? If y'all don't mind, I'm going to switch to.
All right, let's try it. It could, yeah. Let's. Yeah. That works.
One moment. Okay, how's that?
That's very good. If you shake the table just to make sure that perfect. No sound.
Okay,
great. Thank you so much for telling me. I appreciate it. Okay, so again, we're going to focus on this send a suggestion versus not. And in the first version, V1 of Hard Steps, this was micro-randomized. That means that it was just, there was just exploration. It was sent with probability 0.6 at each of these 5 times per day. It was a little bit more complicated than that, but generally that was the idea. It was an 0.6, probability 0.6. And the reward, the goal is to impact the individual's near-time behavior. I mean, that's the most important outcome. And the reason why is the content of that message is tailored to helping the person be more active at that moment in time. If you think of how the data might look in one of these studies, on each user, you have this time series of examples or tuples, state S, action A, reward R. Again, it's 5 times a day. In V2 and V3, one was 3 months, the other was 9 months long. The state is the information that's coming up on the sensors with the tracker, the wristband tracker, as well as the smartphone. Action is binary, as we already discussed, and then the reward here. At the bottom of the slide is a critical piece of notation, and that is the expected reward given the current state and current action. Remember, the action is binary, send a suggestion versus not, is abbreviated by lowercase r of SA. And I'll use that repeatedly in this talk. So I'm going to go on to the algorithm we used in V2 and V3. It was actually deployed in those 2 studies. So during the study, this algorithm selects actions, send a suggestion versus not, with the goal of maximizing the total steps, 30-minute steps, subject to some constraints. And these are pretty ill-posed constraints. The first constraint is to ensure that you can, not only would you learn, that is, you would learn which action is best as you experiment on that individual during the study, but you need to learn between studies as well. You need to facilitate off-policy learning and causal inference. And that does impose a constraint on the behavior of the algorithm. The other important, more from a domain science point of view, constraint is that you just can't send suggestions all the time. People become overburdened by these suggestions if they occur too frequently or in the wrong locations. So what we did was let me just mention, so this means we're really not going straight for regret minimization. Instead, we're looking to personalize as much as possible within these constraints, these relatively ill-posed constraints. You'll see how we operationalize it here. One definitely should be able to do a better job. So what we did was we deployed a generalization of Thompson sampling banded algorithm. And I say it's a generalization because it does look into the future and try and assess the impact of increasing user burden. So I'm going to give you highlights because this is not the focus of the talk. I just want to give you enough about the algorithm so you have an idea about what was run. There were two elements of this algorithm. There's the Thompson sampling banded algorithm. The first is the learning algorithm, and this is the algorithm that's being used to learn the reward function. That is this expected reward given state S and action A. And what we used was a Bayesian linear regression model. That's a very simple version of a GP model. And then the second element of this banded algorithm is how the actions are being selected, the binary actions. And what we use is posterior sampling. That's in accordance with Thompson sampling. And here the idea is that you calculate the posterior distribution of the following. So what is the advantage? That is the reward in state S. If you send a suggestion, that's 1, minus the reward in state S. If you don't send a suggestion, that's 0. So you look at that advantage of sending a suggestion in state S. Does that exceed the threshold? A threshold. You calculate the posterior probability of that advantage exceeding the threshold, and then you use that posterior probability to do your randomization. If that posterior probability is high, then with high probability, you end up sending a suggestion. If that posterior probability is low, with low probability, you send a suggestion. So what is that threshold? That threshold was built primarily off of V1, the first of the 3 studies. And if you're familiar with Markov decision processes, you probably know what the threshold is. It is a proxy for the value of next state if you send a suggestion versus if you don't at this current time. So this bias term will be positive if this proxy indicates that there is likely to be negative delayed effects of sending a suggestion now. It'll be positive. And so it's even harder for the advantage. The advantage has to be even higher before you send the suggestion with any reasonable amount of probability. So I just want to give you 2 highlights, one about the learning algorithm and one more about the posterior sampling. So as I mentioned, the algorithm is just using a Bayesian linear regression, but in specifically what we mean when we say that, we're talking about a Bayesian linear regression for the advantage. Remember, this is the average reward in state S. If you send a suggestion, that's 1 minus the average reward in state S if you don't send a suggestion. So we parameterize that by just a simple linear combination. Theta is only 5-dimensional. There's 4 features, and then there's an average. The first feature is like an intercept. It's an average effect of the action of sending a suggestion versus not. I'll show you the features later. We also used an informative prior on theta, this 5-dimensional vector, in accordance with Thompson sampling. It's a classical Thompson sampling. It's a Gaussian prior, and that means we had to pre-specify the prior mean and the prior covariance matrix, and this was built off of the first study. Further, when people came into the second 2 studies, they had a week where there was only exploration at each of the 5 times. They were either randomly assigned a suggestion or not with probability 1/4. And so that data also was used for that particular, on each individual to update that person's prior. The other element was the action selection strategy. And so just to recap, you think of the advantage of sending a suggestion versus not. It's parameterized via this 5-dimensional weight. And you calculate the posterior probability that advantage exceeds the bias term. So I really made some big mistakes when we first started this study, and we had to end up delaying the start of the study. And this is because I didn't think about this first question. So in some states, this Gaussian, the distribution of the advantage minus the threshold will center at 0, indicating that the data so far is telling us that the advantage isn't sufficiently enough to warrant sending a suggestion. There's very little information that it's worth it to send a suggestion. Then what happens is standard Thompson sampling, what it does is it randomizes with a probability around 1/2. Is this a good idea? Current data on the individual is indicating that the individual is not receiving sufficient benefit, and we're going to randomize with probability 1/2. That's a bad idea. We're going to aggravate them. The other second issue that we realized, well, of course, we knew the second issue ahead of time, was that we have to permit these causal data analyses after the data collection is over. So both of these motivated us to alter the algorithm, and we restarted the study after we altered the algorithm. So what we did was we used a very crude approach. We essentially, we follow this little blue graph, which I've drawn here. Across the horizontal or x-axis, you see the posterior probability of sending a suggestion. If it's around 1/2, what we do is we shrink it to 0.2. If the posterior probability of sending a suggestion is around 0.8, it gets shrinked to 0.8. So in between, so the posterior probability that's actually implemented online is always between 0.2 and 0.8. So how did we get these numbers? So 0.2 is the lower bound, that's that P sub L, and 0.8 is the upper bound. So 0.8 comes about by a team discussion about how often you want to send a suggestion if the current data indicates it's really worth it. In that state, the current data indicates it's really worth to send the suggestion. How often do you want to send it? And we decided, okay, 80% of the time. 0.2 comes about by thinking to yourself, well, the current data is not indicating a lot of evidence for that, sending that suggestion. How often do you want to send it? Understanding that you need to continue to learn, it could be that in particular states, you might begin to see an effect. And we decided, okay, 20% of the time you would send it, even if there's little evidence that it's effective. So this was our strategy that was actually implemented. Okay, so I'm going to go over the algorithm. Oh, no, I'm done. So now I have to pause. I'm supposed to pause. Do you have any, is there one or two clarifying questions that people want to ask me?
So we have in the chat, Susan, Deborah Dubashi is asking why this variant rather than the usual TS for posterior sampling?
Sorry, Susan already answered that.
Oh, so, okay, yeah. That's indeed. And we have another one. Did you see any MDP setting here?
Can you state that question again one more time?
Did you see any MDP setting here?
Do you use any MDP setting here?
Yeah, so of course, what I really want to do is use an MDP setting. Let's be honest. The problem is we all know that predicting the value of next state is really hard. And it often gets, by hard, I mean, it's predicted with great variance. I mean, this is the perennial problem in RL, is that the predictions of next state, the value of next state, are high variance. And so what happens is that means the target, which is like in TD learning, for example, the target now is your current reward plus your prediction of next state, the value of next state. And if that target is high variance, you learn even more slowly than you would otherwise. So this is really due to a bias variance trade-off. And of course, we wanted to do something like a full MDP. That's why we brought in that bias term that we constructed. So essentially, we got a proxy for the value of next state, but we built it completely off policy from prior data.
Thank you, Susan. So we have two more, but perhaps you want to continue. Maybe I just state them and you can address them as you go. So the first one is, what information is contained in the state? And the second one, would there be better ways to choose the lower and the upper bound?
I just want to say I'm positive there's better ways to make this whole constraint issue work. Positive, because this is really a constrained optimization problem. And so you want to mathematize your constraints in a way that makes domain science sense. And what we did was we just took a poor man's approach and we did the clipping of the probabilities. We've got to be able to do better in future. That's totally clear. And I forgot what the other question was.
So the first one was what information is contained in the state?
Yeah, we'll see this shortly. We'll see, at least we'll see there's a good bit of state information, but we'll see the 4 features that are used in the advantage shortly.
Thank you, Susan, and thanks for those questions. So let's continue ahead.
Yeah, so what we want to do is we ran in those V2 and V3. This algorithm was implemented on 91 users, about half from V2 and half from V3. Again, it's choosing send a suggestion versus not. And so our lab has developed primary analyses that are used in clinical trials for this type of setting. They don't make hardly any assumptions. I'm not going to use those kind of analyses here. What I'm going to do here is I'm thinking in my mind, how might I think about it? These are more secondary analyses that one might run. And here I'm going to use assumptions in order to address this question of personalized digital health. And so the very first question I'm going to ask is there evidence just on average across all states, across all individuals, that there was an effect of sending a suggestion versus not on the individual's subsequent activity level, their step count? Now in V1, there was a very strong effect. So we want to know, is this happening here as well in V2 and V3? Yeah, and then we want to look at heterogeneity. So do some users benefit a lot more from these suggestions, or some states in which the suggestions are more beneficial? So when we first started down this, we were pretty much at a loss. I mean, I didn't know how we would address these questions within a bandit kind of environment. And what we ended up doing was we adopted a very, very old methodology. That's what I'm talking about next. This is classical meta-analysis. Now, we're not talking about meta-learning here. This is meta-analysis from old, very classical meta-analysis from the clinical trials literature. Meta-analysis is, to this day, is used across the world in order to synthesize results from multiple clinical trials about different types of medications. And you see a reference at the very bottom of the slide about this, just the data that reference. This was it was a very mature field in 1999. Okay. This is a great reference, very well written. We're going to use these ideas. So in classical meta-analysis, you have multiple clinical trials and you want to combine results across each trial. Here, what we have is we have 91, we're going to think from a bandit environment, we have 91 clinical trials. Each trial has a number of tuples, and that's what's written at each user is a clinical trial that donates a number of tuples. The tuples, that's examples, state, action, reward examples. So each user has, in this classical world of meta-analysis, each user has an unknown set of treatment effect, 5-dimensional set of treatment effect coefficients. This is what parameterizes the advantage of sending a suggestion versus not. And we're going to denote that with a subscript of 0, I for ith user. Then what you do in this world, this classical meta-analysis world, is you create from each clinical trial, we have 91 users, 91 clinical trials, you create an estimator of these unknown treatment effects, 5-dimensional vector. And what we'll use is the vector of posterior means it's available at the end of the study, that user's end of study. We used Thompson sampling here. So this means this posterior mean, this theta hat I, it's just an L2 penalized least squares estimator. That's all it is. It's just the L2 penalty term is determined partially by the prior, the tuning parameter on the L2 penalty. Here again, you see the advantage, and there's 4 features which I'm going to show you shortly. Okay, so in classical meta-analysis, we have 91 trials. There's 2 ways to think. The first is you're only interested in these 91 trials, these 91 specific users, and you just want to make statements about them. So in this case, I think of this L2 penalized estimator 5-dimensional vector theta hat I as having an approximate normal distribution with the each user's unknown set of weights for their advantage function. And then of course, there's a covariance, because we're not observing this user indefinitely. We only have a finite number of examples from each user. The second way to think is that the 91 users represent a sample from a population of users. And you want to make statements about that entire population. So this is more about generalization to a larger group of users. And actually, in this particular study, HeartStaps, this makes a lot of sense, because these individuals were all at Kaiser in Seattle, and as soon as they were diagnosed with stage 1 hypertension, they were asked, would you like to go into this study? So for example, if Kaiser were thinking about, this is a big health maintenance organization in the Northeast in the States. If Kaiser thought about rolling this out in future for their patients who are newly diagnosed, they would be interested in this type of population-based inference. In this case, you make an additional assumption. That is, the users themselves are sampled from a larger population. So the theta sub pop is the average of that 5-dimensional weight vector for the reward function across the entire population. And then, of course, there is some variance in that effect across people in the population. Okay, so let's just look at the green table first, because someone asked about the features that are being used. So there is 5 lines, 5 rows in this green table. They correspond to the 5 features. The first is the overall effect of the action, sent a suggestion versus not, and that's averaged over the state, the context. Then one of the context variables was a measure of how often that individual had been sent a suggestion in the prior week. The higher, the more suggestions that were sent previously. So this is a constructed state feature. Engagement was whether or not the individual was more engaged on the prior day than they usually was. And engagement here means they're going to the app of their own volition and they're self-monitoring their behavior. Location means whether or not they were in a structured environment. Structured environment here means they were at home or work versus somewhere else. And step variation, this was something we thought had great promise, and it didn't pan out at all. This was whether or not over the prior 7 days, in that same time interval, that individual had a lot of variability in their step count. We thought that if the individual had a lot of variability in their step count, they would probably be more receptive to a suggestion now, because high variability would mean that they had a lot of room in their schedule for changing their behavior. It didn't pan out. Okay, so let me just tell you how I got the second column of that green table. So first of all, this E here, this is just a one-hot vector, and what it does is it just picks out each of the 5 entries of theta hat. That's all it does. This product is just picking out each of the entries. So we get a estimator of theta hat pop, the population average on average across the entire population for each of these 5 weights. The way you form this estimator is it's a weighted average, and the weights are associated with the with estimates of the within-person variation across their own examples, as well as the variation from user person to person across the 91. And you can form a confidence interval. This is all very classical statistics, and it comes straight out of that reference that I provided to you on the prior slide. So I'm giving you the confidence intervals in this second column. When we saw this, I was very happy at first because the first study had indicated there was a really good effect of sending a suggestion as opposed to not. And indeed here we see that there still on average appears to be an effect. It's a positive weight. And the confidence interval doesn't contain 0. But when you go down to the next row, you realize things don't. So this is on average for the population level. This is not about the individuals. You realize when you go to that next row, you see that negative coefficient of -0.3. This is a disaster. This means that if there's any reasonable amount of dosage, that is prior treatment, it kills the effect of sending a suggestion now. And I'm going to show that. That's going to become clearer on the next slide. And all the rest of the features that we thought were going to be really great, I mean, the whole scientific team, on average across people, there just doesn't seem to be much going on. So to drive home this point more clearly, here I'm going to look at the evidence, overall evidence across the population in a particular state. And this state is, that individual has received the average level of interventions over the prior week. They're currently pretty engaged. They're looking at their app. They're at home or work that's in a structured environment, and they haven't been that variable in their activity recently. And you see that confidence interval, and indeed it contains 0, just driving home the problem with dosage. The minute someone had gotten a lot, on average across people, if there had been very many prior suggestions, responsivity to the next suggestion, on average across people, doesn't look so great. Okay, so now we went to the next question we wanted to ask. Well, is the better action user specific? And also state specific. And this in the classical meta-analysis is usually done for the actual 91 users. It's about the 91 users in front of you. And what this does is that you form a test statistic based on the variation in the weights across individuals. Again, this little e is just a one-hot vector, just picking out each of the 5 entries one at a time. And you form a weighted sums of squares. So it's a weighted variance. And the weights are according to the within user variance in their examples, their tuples, state action reward tuples. Again, very classical. And here you see the results. So with p-values in that very last column, indicating there's a good bit of heterogeneity from one user to the next in terms of responsivity, in terms of the advantage in particular states. So this is what I've taken is a really classical statistical approach to looking at these, the overall effects of sending a suggestion versus not, and how that suggestion differs from one state to the next. And that's I do that by looking at each one of the weights in the 5-dimensional feature vector, weights for each of the 5 features. Another way is to allow for the amount of time people are spending in certain states to influence that comparison. And that's what I'm going to do next. On average across the population, does the banded algorithm select more effective actions than the prior? The answer to this question is influenced by the states people find themselves in. So if people tend to be in more adverse states, even if there's particular states where it's a great idea to send the suggestion, if that state occurs rarely, then that's going to reduce this average effect. So at the bottom of the slide, you see this is more about off-policy estimation. So the average reward for policy pi on user is just the expected reward. Remember, the reward function is the mean of the log of the 30-minute step count given current state and current action. So when you think about this expectation is over the states the user is visiting, as well as the policy that was used to select actions during the study. We use Thompson sampling, which is a stochastic policy, so there's variation also in that policy. So this expectation is both over the variation in the stochastic policy, as well as variation in the state, the way the states are being visited. So we use pretty classical approaches to off policy. One could improve this. This is well understood now at this time. So first of all, we have an estimator of the average reward under the banded algorithm. So the banded algorithm is deploying a time varying policy, because the posterior sampling probabilities are varying with time, and that's what these B's represent, is those time varying posterior probabilities. So we just take the average of the rewards for that individual. And then we wanted to compare that to the average rewards if we had just used the prior policy. Why does this make sense? What we could have done was just use V1, use the data from Hartstepp's V1, create a policy, and just deploy it in future. That would have saved us a lot of time and effort. No need to build some online learning algorithm that's potentially unstable and causes all kinds of software engineering problems. We could have, avoided all of that. So we wanted to compare the performance of the banded algorithm, the learning algorithm, with if we had just gone with sampling actions according to the prior probability. And here we use an importance weighted estimator. Again, there is a way, it's well understood now, you can improve this estimator. This estimator has slightly higher variance than one would. You could get better estimators, but here we're just going to continue on. So we get this estimator value for each individual. That's why they have a subscript of I, and we have 91 individuals. So now the theta in the classical meta-analysis from clinical trials is just one-dimensional. So each individual's theta, true unknown theta, is just the value of applying the banded algorithm to that individual minus the value of applying the prior to that individual. And our estimator is the estimators I gave you on the prior slide, these importance weighted estimators for that difference in values. So again, because we only have a certain number of tuples or examples per user, we have an estimator, and that estimator has variability because it's a finite number of tuples per individual. So that's why there's a sigma I here. And we assume it has a normal distribution. Under certain settings, the asymptotics works out that you do have a normal distribution. And then we also say, well, the users could be sampled from a population, a broader population. So their true underlying weight, theta, difference in values, varies from one individual to another in the entire population. Okay, so here's the exact same sort of analyses that I ran before, but the first is, on average, across the population, do we anticipate that the banded algorithm will do better than the prior? And here, this is a small effect. It's about an increase of about 20 more steps per 30-minute time period. And we suspect this is mainly due to the fact that the banded algorithm is backing off when there's a lot of dosage. Remember, the posterior probabilities would decrease. I showed you the theta hat I's from the banded algorithm. And as the prior dosage increases, the posterior distribution advantage gets lower and lower, decreases. And the prior, because it was built off of V1, was very optimistic. And then the second question we looked at was if we just focus on these 91 users, did the average reward between the bandit algorithm and the prior policy vary a lot from one user to another? Could it be that for some users using the bandit is really worth it and others much less so? And this test statistic was grossly, I mean, it was extremely high, indicating enormous amount of heterogeneity in terms of the benefit of running a bandit algorithm from one user to the next. And indeed, when we looked at the data in more detail, this becomes very clear. So I have two last questions. And the very last question, question number 7, is what motivated all of this work. I hope you find it as interesting as I did. But before that, I think it's worth looking at question 6. On average, across users, does it appear that the bandit algorithm learns over time? Now, what do we mean by that? The prior distribution built off of V1 indicated there was really a strong effect of sending a suggestion on average across all contexts, across all states. But all of the analyses I've shown you up to now indicate that the bandit learns on average across people. There's not much going on average across people. So will we see this replicated here? And if so, how fast will that bandit algorithm learn that the prior on average across people is wrong? That's what we're going to look at now. So on average across users, does it appear that the bandit algorithm learns quickly? So the blue curve is real data. It's the average posterior mean of the treatment effect, that is the advantage of sending a suggestion versus not, in a particular state. And the state is written in that second bullet point. It's the state we've been looking at this entire time. That's the blue curve. And let's focus on the figure on the left-hand side. I'm going to bring my pointer there. And again, we're just looking at the blue curve. The blue curve starts around 0.47. The prior mean for overall of sending a suggestion versus not was 0.47. All of these curves start at 0.47 because that was the prior mean. That's how the whole algorithm gets warm started. And then we see the posterior mean, it just plummets down. How fast is that? Is that decrease really fast? So to think about that, we created these alternative scenarios of where the ground truth is that the prior treatment effect is in fact true. And we created 2,000 versions. So this is a bootstrap. So I have to explain what this, so I'll first give you the overall. So we have 2,000 trials, each of 91 bootstrap users. Each black curve is a curve, is the average posterior mean of the treatment effect in that trial. Each trial is 91 users. There's 2,000 trials. This is in a scenario in which the ground truth is that the prior treatment effect is true. The prior was correct. The way we do this is operationally is we have our 91 users. Each one has a series of state action reward, state action reward. From each reward, we subtract the posterior mean for the reward function in the current state. And we end up, for every user, all the 91 users, we end up with state residual, the difference between the reward and the posterior estimate of the reward function. So we have, for each user, we end up with state residual, state residual, state residual. And we have 91 trajectories like this. We sample with replacement, that is bootstrap, and collect 91 of these trajectories. And then for each of the collected 91 trajectories, we run a bandit algorithm. If the bandit algorithm says, send a suggestion, we add back to the residual the reward function that you would get if the prior were true. And if the bandit algorithm says, don't send a suggestion in a particular state, we add back what the prior would have said would be the case in that state as well. So it's under the ground truth that the prior is correct. So there's 2,000 black lines here. Again, each one represents a study of 91 users under the ground truth that there's the prior treatment effect, the prior is correct. And you see really rapidly that our actual study, the blue line, gets below the variation represented by all the possible kinds of studies you could have gotten if the prior was correct. In fact, within 30 days, on average across users, the bandit is learning that on average, there's just not much going on. It's really nice. So very quickly. Okay, now the last question. This last question is, we found after the study was over, we would look at different users, and there were a whole bunch of users with incredibly interesting results. It was extremely exciting. And I'm going to show you one of these users. The problem is, are these results spurious? We ran a stochastic algorithm. We know that even if you draw random numbers between 1 and 10, you can get a long run of ones just by chance. Okay, so here's one of the users. Remember, this is going on in Seattle. I'm going to talk about the horizontal axis first. So this individual came into the study in mid-November 2019 and departed at the beginning of August in 2020. Seattle closed down due to the pandemic around the end of March. You can really see that in this user's behavior. The vertical axis, the y-axis, is the posterior mean divided by the posterior treatment effect in that individual's current state at that time. So the height of the dot is the posterior mean divided by the posterior standard deviation of the treatment effect in that user's current state. And this ratio directly informs the probabilities with which the posterior sampling. So every time you get a dot that's above 0, that means you can interpret that as the data appears to indicate that it's worth sending a suggestion. Dots below 0 indicate that there's not as much evidence that it's worthwhile to send a suggestion. We color-coded the dots. The blue dots are when the individual was engaged on the prior day, looking at the app of their own volition. The red dots are when the individual wasn't looking at the app on the prior day. So I saw this and I thought, whoa, this is fantastic. We have phenomenal evidence of personalization. Get grants now is, I'm going to be able to get a ton of grants. I'm going to be able to run around and say, everyone should be personalizing, wonderful. But I have to ask myself, could this have happened by chance? Could we have seen these beautiful results in which it looks like every time the person is engaged, it's much more worthwhile to send a suggestion versus not? Okay, so we did this exploratory data analysis again. The blue curve is the real data. Notice this time, the blue curve, it's the posterior mean for the interaction effect of engagement. Okay, so we're just focusing on engagement here. It's that theta weight for engagement. The blue curve starts at 0. Why? Because the prior mean for engagement was 0. All of these curves start at 0. And you see the blue curve, it's generally greater than 0, indicating evidence that some evidence that it's better to send a suggestion. What are the black curves? The black curves, there's 2,000 of them, and they're bootstrapped versions of this user under the ground truth that there's no effective engagement. So here now, what we did to get a bootstrap version of this user, we bootstrapped that user's residuals and then ran the bandit algorithm again on that particular user. This is the user whose data we are looking at. This is really interesting because here in December, you see that the blue curve, that is our estimated our bandit's estimated effect of posterior mean of sending a suggestion versus not is it's positive, but it's well within the mass of the black curves. And the black curves could occur if the ground truth is there's nothing going on. And that's striking because when I look at this graph, I thought, oh, you know, we're learning really quickly that the person is more responsive when they're currently engaged. Only as you get closer to the, of course, there is increasing, you know, it's always positive. This is great. There's a, and as you get to the end, does the blue curve really get above the mass of the black curves? Remember, the black curves are under the ground truth of no effect. So now the blue curve is getting really above, and now there is increasing evidence that there is personalization going on here. It's very interesting. An open question is there's just a whole bunch of ways you could summarize or try to ask this question. And how might one do this? This is just exploratory analysis of how to think about it. Okay, this is my last slide. We used a sequential decision-making algorithm to personalize in V2 and V3, but did we achieve personalized digital health? I asked this question throughout this entire talk under the setting that each user is akin to a clinical trial. That is, each of their tuples is like an example in a clinical trial. What we're essentially assuming, that is, we're assuming that their potential outcomes across time are independent within a user. Even if you're willing to make this assumption, how could you do a better job answering this question? Did we achieve personalized digital health? It's clear in general this assumption is incorrect. We didn't see actually a lot of evidence of, once you took into account the features, we didn't see a lot of evidence of correlation across time, but this is just one study. In other studies, we could very well see a lot of evidence for within-person correlation across time and residuals. How do you address this question if this assumption of independent potential outcomes across time within a user is violated? This is really important because in general, we really do want to allow for a Markovian type setting. Thank you.
Thank you very much, Susan, for that very interesting talk. And I'm very curious to hear also what the audience has to say. We have about, what is it, about, less than 7-ish minutes or so, but we can go maybe 1 or 2 minutes over time. So we have Hampus Åström first off. So please, Hampus, unmute yourself and feel free to ask the question.
Yeah, so I had 2 different questions and answer them how much you like. The first one is, you set these boundaries on your probability to 2% and 80%. But I guess for some users, at least, that want like a more organized life, that want to fit into a schedule, maybe on your or on the autistic side, for instance, might want it to always be the same. And when you have a percentage that's never 100 or never 0, you will force it to always be random, which might be bad for the user. Just getting it to the average of like the default being 0.2 might be good, but I would taper those off in the end, so you have some chance, even if it's buffering against stupid decisions by the algorithm a bit. What's your view on that?
Yeah, that's a great question. Okay, so so this is what I'm fixing to say could be very individual specific. Okay, so I recognize that. So there's 2 reasons why I wouldn't want to do that. The first comes out of psychology. There's a whole area of psychology involving reinforcement schedules. And it's well known that variable reinforcement schedules are much more effective than fixed reinforcement schedules. And a variable reinforcement schedule has this amount of variability. In a sense, it's a sense of novelty. This is related to habituation. And you experience habituation, all of us experience it. For example, if I move to a new location where there's a railroad track nearby, the first couple of nights I'll wake up every time the train comes by. After that, I never hear the train again. That's habituation. And so these stimuli that are being sent to you in real life, you just don't see them after a while. If you have a non-variable reinforcement schedule, you get habituated very, very quickly. The second is the novelty. There is some evidence that novelty itself, that is variability, actually improves effectiveness. Now, again, that could be individual specific. Someone who is more on the autism spectrum might want more stability. They might want to get a message at each of the 5 times per day, for example, let's say, if they were effective. The other reason, though, is related to the fact that in these studies, it's not only in these studies, I think actually in real life implementation as well. It is critical that we permit learning not only within a user, but across users. And the more we allow those probabilities to get closer to 1 or 0, the more we disallow learning between studies. And in fact, sadly, I am doing so many gross simplifications. These are non-stationary problems. We're
Yeah,
not.
that was my second question.
Yes. These are for, and the problem is we don't sense my rationale for why I think it's non-stationary is that we don't sense the full state. Our sensors are just not there. They're just not there. Even if you have a wearable that has, like a t-shirt that has a little instrument in it, we're still not getting the entire state. So it's going to appear as if the effectiveness of the action is varying with time, when that's just due to the fact that the individual is moving into states that you don't have complete observation of. And so these are really not straight up MDPs. They're really tracking problems. And so my feeling is when we go to implement, we don't want to have the probabilities go down to 0 or 1, go up to 1 or down to 0, because they're inherently tracking problems. And we always want to get as close as we can for that person at that moment. How we mathematize this, I don't think we really, it's like continual RL, right? How do we mathematize this? This is not clear to me at this moment. It's a great question. I mean, yeah.
All right, thank you. And I think you partially covered my other question about the fact that the human is also learning at the same time, and that might really mean that your your bias in one part of the time series might be very different from the other part, and
yes,
treating it as the same all the way through is probably not correct, because people get used to the thing,
exactly.
like you said. So
yeah. In fact, what we're trying to do now, I don't know if we'll be successful, I have to be honest with you, but to construct the features, right now we use domain expertise and some analyses of prior data. But I really think we should, since we are interacting with another agent, that is the user, we should probably try and use some ideas from RL out of cognitive neuroscience to construct the features. You must have realized, yeah. That's certainly an area I'd like to go towards.
Cool, thanks.
Yeah.
Thank you, Hampus and Susan. Is it okay, Susan, if we take 1 or 2 more questions, or?
Of course.
Great. So please feel free to write in the chat or just raise your hands and or unmute yourself.
I see Frederick has.
Thank you for a lovely talk, Susan. That was very interesting. I was just about to ask, actually, you touched on this in your last comment here. So you asked a very introspective question here. We did something, did it work or not? And I was curious if you did this again, what you would change, because they're both in my mind methodological challenges here, but there are also sort of fundamental questions surrounding what kind of effects do we expect from these interventions. Yeah. And so I was just curious about your thoughts on this sort of broader picture of the types of study that you do.
Yeah, so we do have these classical clinical trial analyses that you use for these types of studies. And they're analyses that don't make a lot of assumptions. And we are finding, so there's a whole legacy or whole background for standardized effect sizes in clinical trials. And we thought our effects would generally be much lower because these are so momentary, these interactions. But in fact, we're seeing effects on the size of a usual clinical trial. So if you go back to that literature, there's standardized effect size. So that by standardization, you mean you divide by the standard deviation of the residual. They're about on the order of 0.2, like 0.5, 0.8. So I'm beginning to think that some of the intuition from clinical trials will translate here as well. We're also, so when we size these studies, we have to determine the number of users. So there's two ways you end up in these kind of studies. You're either in a study where it's being run in collaboration with investigators at a med school, and this is much closer to a clinical trial study. You have to determine the sample size in order to make some guarantees about what kind of results you're going to do. And there we're much better at getting the sample size now than we used to be. That's great. Yeah.
All right. Thanks a lot.
I've learned a lot. I mean, all I see is open problems. You know,
I realize it's difficult to condense in one answer too, but yeah, it's fascinating work for sure.
Thank you, Frederick. Susan, I think there's another one in the chat by Elasto. If you want to unmute yourself and ask your question, if you're still around.
Yes, please, if possible, yes. So the question was about least squares method. So you mentioned that you use least squares method with constraints, and I just wonder how the properties of the least squares method may be affected by the constraints. That is the first question. And the second question about singularities in the least squares method. So have you met any singularities in the least squares method when doing this work? Thank you.
Okay, so Thompson sampling is it's a Gaussian prior, a Gaussian model for the reward. So the posterior mean is actually the solution of ordinary least squares with an L2 penalty term. And the tuning parameter on that L2 penalty term is related to the prior variance for each of the weights. Okay, so you asked about singularities, and I think what I really need is to know what we mean by singularities, because there are things that I would call singularities, but I suspect, so when I say this is a very smooth penalty function, it's an L2, it's not L1. I'm not using L1, thank you.
Yeah,
I'm not doing anything non-smooth to this data.
Yeah, that's true. The singularity, what I mean under the singularity. So in the least squares method, you're supposed to solve the normal equations, right? And there you have, that's what we call, it's generally called Fisher information matrix.
Right.
The Fisher information matrix may be ill-conditioned matrix, singular matrix. So not singular, hopefully not singular,
yeah.
but ill-conditioned could well be. So have you met any numerical problems in your studies? That was the question. Thank you very much for your presentation.
Yeah, I got it now. No, actually that prior, it accidentally regularizes the design matrix, so that the design matrix, you don't see a lot of collinearity or close to so the eigenvalues of the design matrix, because you're regularizing it by that prior. It's really, Thompson sampling is amazingly stable. It's amazingly stable.
Thank you very much.
Yeah.
Thank you, Susan. So I have one question. So if you would start over your study today, what would you do differently? And moving forward, what's the next steps here in your research?
I would like to I'd like to investigate that proxy for the delayed effects and do a better job there. I would like to, right now, the thing I'm really focusing on at this moment in time is this algorithm was run separately on each individual. 91 individuals, 91 times. It's clear that some individuals in some states respond similarly. So is there a way to pool the data online so that we can learn faster on each individual? How do you do this in some intelligent way? Pool data. So, and it's not similar individuals, it's similar individual states, right? Individual cross state kind. And I've been wanting to do this for a long time, but the problem with that is that after the study's over, we must be able to do after study learning. If you pool across individuals during the study, all of the classical importance weighted methods, all of that dead. All of the, there's no theory. So right now, we have a paper we're writing up to submit. It's a very theoretical paper, but it's about how you can do analyses to that kind of data. That then will allow me to justify running a study where I run a pooling algorithm. So I wanted to run a pooling algorithm a long time ago. I wanted to focus on that, but you can't justify, you got to raise this. You just can't do these studies willy-nilly, right? Yeah.
Yeah. So that's before I ask my follow-up question, maybe Frederick, you can jump in here. I think it's related to this, right?
It is definitely related to this. Thank you, Otto. So you mentioned pooling here as a way of sort of learning from many people at once, I suppose. I get I have an interest in banded learning and reinforcement learning myself, and something that we're thinking about is exactly how can you personalize something quickly? How can you quickly learn to pick up the behavior of an individual with a banded, right? And I think from my own perspective, it makes sense to think of learning a prior from a collective and then sort of personalize. Is that something that you think about?
Yeah, so the whole prior, the reason we used the prior was the hope that if these were similar enough individuals, so that every new person, they may not be really following the prior we constructed, but it's like a warm start in an optimization problem, right? So, and we could more quickly find good weights for that individual. So that was the whole purpose of the prior in our, it wasn't to regularize.
So what I meant then is, maybe you can speak to the what you would gain in terms of the pooling, as opposed to, like, for me, that they are serving similar purposes a little bit, but maybe that's not how you view it.
I think they are, but the problem is within a person, the noise level, because you're experimenting as they go about their life, is massive. And people, if you go to digital intervention, that field, in real life, people disengage really fast. So it's like there's this timer going on between your agent and the user walking off. And I'm looking for every way that I can improve or warm start this optimization algorithm. This is how I view it. This is an online optimization algorithm, and the more I can warm start it, the more I can speed up learning, the better.
Yeah, no, that makes a lot of sense. And I'm glad you brought up the noise levels, right? Because that's something that's somehow very tied to the type of application that you are working with, where, I don't know, it's hard to keep somebody engaged, as you say, and have a regular kind of feedback that's noiseless enough. Super interesting.
And things happen in their life, like even if they're totally engaged, all of a sudden their child gets upset and they can't react to anything, so very noisy environment.
Thanks a lot.
Thank you, Frederick. So before I let Hampus ask perhaps the last question, I'll squeeze in one here in between. Is that actually related to this sort of thing? You mentioned the pandemics occurring during the experiment, which wasn't expected, but we are assuming stability in the system, in the causal system in general, right, from beginning to the end. And so the variables that you've collected are sort of tuned towards the starting state. But then you have an intervention which was totally unexpected, the pandemic, so the causal system gets modified. And so I wonder how this modification, basically how you account for it. It's learning. I mean, you talk about learning across individuals, and I'm thinking just learning when the causal system changes throughout the experiment. So can you speak a little bit more about that, how to actually incorporate that change in the causal system as you learn?
Yeah, originally we thought we would put a Gaussian process prior on the weights, which results in exponential discounting of data into the past. That's what a simple Gaussian process prior on the weights results in exponential discounting of prior data. Right now, I don't know. I mean, we'll see how it goes forward. But right now, the noise level in the data is so high that you continue to explore. The algorithm is not settling down. Like it's not settling at 0.8 or 0.2 probability like I thought it would. I thought it would settle down really fast, and it's not in general. So I don't have, yeah.
Yeah, it's a difficult problem. And after all, I mean, you only have 92 cases. I mean, you could, you know, I mean, maybe you factor that by 1,000 and you have some stability or so.
Right,
That's the problem of recruiting and having
yeah. Yeah, and these are all people with clinical problems. So like if you go to wellness, then there you might be able to get 100,000, 200,000 users. But the problems are a little different there. They're even less engaged. I mean, these people are people who have an illness. They've been diagnosed with a problem. So I'm not sure, you know, I don't know.
Yeah, these are difficult ones. So Susan, we have one last one, Hampus. I guess you were ignited by some of the discussions we had here. So the last question goes to you, and then I would like to thank you also, Susan, and then hand over to Frederick to say something in the end here.
Yeah, I'm also asking on the same topic here. So I was just wondering, like, I mean, your data set is fairly small here, just 91 people. But even then, if you want to share the stuff while training and still get separate sets, do you think it would be viable to like split them into 10 piles and have 9 individuals in each that share a reinforcement learning agent that knows which of them is who, so they can personalize, but they have a backbone that they share? Or would that also still ruin your data analysis, even if you would have 10 different options instead of date 91, but it would at least let you share, I mean, 10 times as much between them?
Exactly. Yeah, so you would end up with only, say like you had 10 clusters. Suppose you clustered when according to some baseline data, and you end up with 10 clusters. Then you have 10 independent units of data at the end of the study. You're dead for classical statistics. Now, that said, the work we're doing now is going to be able to manage that. Okay, so I don't want to, you know, so if you blindly follow the kinds of analyses that people are accustomed to in clinical trials and familiar with, there's a problem. So, so actually, we were planning, we have this dental health study that's about to go into the field, and we were going to put people in clusters of 5. Then we'd ended up with like 30 clusters. And we thought, oh man, we can do some analyses, but now I'm thinking because of the theoretical work we're doing now, we won't even have to do that. The issue with the clustering is more complicated also. In most of these studies, people are incrementally recruited into the study. And so like, for example, let's say I want to cluster just on gender. So I'm only have 2 clusters, just traditional gender, men and women. What happens is because people are coming in incrementally, and it may take a while before I have enough women, like the first female in a cluster, I don't have any data to share with her for a long time. So the incremental recruitment is really problematic in this setting. It really makes it problematic to do baseline clustering.
I was more thinking random clusters, to just cluster them by timestamp or whatever you want.
Yeah, actually,
so you can compare them as if they were identical experiments rather than based on some metric.
Yeah, actually that's what we were going to do too. But now I'm thinking we won't have to. I want to, if we can do some sort of more smooth types of sharing information across users, if we have our primary analyses straight so that we can do that, that's what I'm thinking I want to do. Because that's a smooth processing of the data, whereas clustering is a discontinuous processing of the data. And the more discontinuities I introduce in the data, the more chances you get for funny kind of instabilities and after study analyses. This is a classical problem, for example, if you use lasso and well known. So I want to use something, I want to use smooth operators on the data to the extent I can.
Thank you, Susan, and thank you, Hampus, for that last question. So Frederick, please, the floor is yours.
Sure, thank you so much. As you know, this is an ongoing series, and we have some exciting events coming up. So stay tuned for that. You'll get an email if you're subscribed to the mailing list. With that, I just want to end by saying yet again, thank you so much, Susan, for your talk today and for your answers to the questions.
Yes, thank you. I just put it in the chat.
Yeah, perfect. That's all from us today, and we look forward to seeing you all in the audience soon again. Bye for now from Chalmers AI Talks.